graphing to solve these equations. Okay, so if you're using graphing to solve any kind of equation, the same thing happens. You plug one side of the equation in to one line, you plug the other side of the equation into a separate line. You do not put the equal. You can't put it all on one line and put the equal. You got to put them into separate lines. And what are we looking for? The intersection. Okay, we are looking for the intersection. Now, remember when we plug into Desmos, we can't use the A's, we need to use X's. So 1 over X minus 6 plus 4 over X squared minus 6X. Okay, we put that in, then we put in the other side of the equation. What was it? 1 over the same thing, X squared minus 6X. Now, this one's a little funky because the graphs have very, very similar shape, but we're looking for their intersection points. So if I click on, say, for example, the purple one, I'm looking for these gray points. Now, they put gray points on a lot of different things. They put them on x-intercepts, they put them on maximums and minimums. So like this gray point right here, that's not an intersection. Those two graphs don't cross there. So that is not an answer that I'm looking for. Over here, this gray point, those two functions, those two graphs do cross at this point. You can zoom in to confirm whether they actually cross or not. See how the closer I'm getting here, you can see that over here the green one was on top, and on the left the green one was on the bottom. So that means they switched places. They had to cross there at that point at -3. Now again, if you have multiple choice answer choices, you can use those to kind of help you narrow down what the correct answer is. But if I look at my graph, there's nowhere else where these are going to intersect. If I look at this piece right here, the green one is always inside of that purple one. It does get close right here, but that's partially because I'm in projector mode, so my lines are thicker. Okay. Same thing over here. They get close, but if I click on the green one, there aren't any gray points showing the intersection over there. They're just gray points over here. And again, I can zoom in to see what they are. That is not an intersection point over there. That's not an intersection point. That's a x-intercept. That is an intersection point. Okay, so -3 is our only solution for number 1. A equals -3. Yeah, I know that was a lot of explanation there, but there were just a couple of things I needed to clarify. If we do number 2, same thing. We plug one side in, we plug the other side into a separate line. So let me do that real quick. Remember, if you need that fraction, do the fraction bar first. So that way you don't have to worry about parentheses. X squared minus 25 over 2x, that's the left side. The right side, 3x squared plus 9x minus 12 over 2x minus 3 over x. Okay, so I've got the left side plugged in, the right side plugged in. I can obviously see one intersection point right here, but I'm really zoomed in on my graph, so I'm going to click the little house to take me so I can see a bigger picture here. I'm going to zoom out a little bit more because I want to see if anything else is happening. Again, these gray points, this one's an x-intercept, okay? That's not an intersection. Those two graphs are not crossing right there. It looks like I've got possibilities over here. I already noticed that one at -3.5. Okay, again, this one's another x-intercept, so that doesn't apply. And it looks like they also intersect right here. Those two graphs cross at -1. They cross at -1, and they cross at -3.5. It is possible to have more than one answer. for these rational equations. Okay, sometimes you'll just have one, sometimes you'll have two. Technically, no solution is a possibility. They could never intersect, and if they never intersect, then it's no solution. But more likely, you're going to have one or two answers. All right, any questions about that? Again, let me clarify. You can use this method for any equation. Anytime there's an equals, plug in the left side, plug in the right side, look where those two graphs cross. I don't care what kind of equation it is, you can use this method. All right, now, there's some word problems that go along with rational functions. So let's look at number 3 and 4 there. It says Jill can wax a floor in 9.5 minutes. Sumali can wax the same floor in 13.8 minutes. Find out how long it would take them if they worked together. Well, there's a little formula for this. And it's the same thing every single time. It's 1 over individual plus 1 over individual is equal to 1 over together. And by individual, I'm talking about times. So 1 over somebody by themselves, their time, plus 1 over somebody by their self time is equal to 1 over their together time. So let's look at what number 3 says. Jill can wax the floor in 9.5 minutes. Sumali can wax the same floor in 13.8 minutes. They gave us both of their individual times. You want to make sure that they have the same units. They're both in minutes, so we're good there. Sometimes they might give you 1 in hours and 1 in minutes. So if they do that, you got to convert the hours to minutes. But here they're the same, so we're good. So 1 over Jill's time, 1 over 9.5, plus 1 over Sumali's time, 13.8, is equal to 1 over, we don't know how long. It says find how long it would take them if they work together. So if we don't know what it is, we use a variable, right? 1 over x. This is just like what we were just doing. Left side, right side. So 1 over 9.5 plus 1 over 13.8. Now, you do have to be careful with this because this doesn't have a variable. Remember, if it doesn't have a variable, we have to do y equals. Okay, we have to do y equals for it to graph. If you don't, then it just gives you the number. So we graph that, and we graph 1 over x, and we can see there's an intersection right there. We don't need to worry about this side of the graph. We're talking about time. We're not going to talk about negative time. So really all you have to consider is the positive side of the graph, the right side of the graph. Look for that intersection point, 5.627. It says to round to the nearest hundredth, so 5.63. And we need units. Anytime we're doing a real life application problem, we want to put units. So it'll only take them 5.63 minutes to do it together. Okay? They can also ask us for an individual time. Mary can mop a warehouse in 10.9 hours. That's an individual time. One day her friend Bill helped her and it only took 5.55 hours. That's a together time. They worked together, he helped her. So that's on the other side of the equation. Find out how long it would take Bill to do it alone. We don't know his individual time. So the x is on that side of the equation this time. So I can leave that y equals, even though I'm gonna have an x here this time. I'm still gonna leave it as y equals, and then y equals 1 over 5.55. Okay? I don't really have to move my graph. I can see the intersection point right there, 11.307. And if we round that like we're supposed to, 11 away.